for the interest. What I would like to do today is that to give you some of the highlight of the information about the seismic design and the behavior of the highway bridges. This one here is a course that we give at the university here. So what I would like to do today is that to give you the most important highlights in like about 80 minutes, so that what you will be able to be really aware of what is the seismic design and what we have learned from the recent earthquakes. This is the outline of my talk. The first thing that I will give you some information about myself, and then I will tell you about how was the behavior of the highway bridges in the recent earthquake. This is extremely important because that's how we learn what is the behavior of the bridge. We can learn from two things. We can learn from the experimental testing in the lab, or we can learn from the field. And when we have an earthquake, that will really give us the opportunity to be able to see how is the behavior of the bridge in a system level. And that will be the real deal, that we know how the details and how the design of the bridge will be actually in real life. The second thing I will talk to you about the ASH2 design specifications and the performance objectives. And then we will talk about the design methods. We have two methods for the design. We have a force-based and we have a displacement-based. And then I will be able to outline for you what are the steps for the seismic design. Some of the brief introduction about myself. I was a bridge engineer and I was the instructor at the California DOT. The California DOT at that time, they used to have what's called the Bridge Academy, so that we used to have the engineers come there for 2 months, and that will be a full time, so that we will be able to give them a complete course in the bridge design and also the analysis and the behavior of the bridge. I'm a licensed engineer and I'm a structural engineer, and I came to UNR in 1994, and I have been here since that time. I was a department chair, and now I'm the associate VPR. The research interest, what I have two main things, is the behavior and the design of the highway bridges, and also to be able to understand that we do a large-scale test. We have one of the biggest labs in the nation. It's a bridge engineering lab, mainly dedicated for actually bridges, the design of the lab and the loading and the actuators and the shake tables that we have. It's really dedicated for a large scale type testing for like a bridge type. These are series of some of the experiments that we have done. The first one on the right, that is extremely important. This is a rebar cage that we have failed on purpose to be able to see how the behavior of rebar cages during the construction. As you know, we are not allowed to have any splices in the columns at the ends of the column. Where do we expect to have a plastic hinge? So they tend to have rebar cages that will be standing up, and they will have guy wires for these. And recently, because of the construction methods and means, we started to see failures and also, unfortunately, death when you have a failure like this. So we have started to do the investigation on the behavior of these cages and how we really prevent them from the collapse during the construction. So these are the rest of the photos. These are series of the shake table test, the one that what you see at the top left. These are the 3 shake tables at UNR, and that's where we put the bridge on top, and we shake the tables to be able to understand what will be the behavior. The photo in the middle, this is here part of the San Francisco-Oakland Bay Bridge, and that's what we wanted to see, what is the behavior of of a perforated plate member. It's a steel member with the perforated plates. The photo on the bottom left, this is what you see, a steel plate girder bridge. It's a two girder with a deck on top. This is here a composite deck. So you have shear connectors that will connect the reinforced concrete deck to the plate girders. And the main thing here, what we want to see, the load path. So what you're gonna hear us, myself and also Dr. Saiidi, we talk about load path, and this is extremely important so that we will be able to see what will be the flow of the forces through the elements of the bridge. Most of the weight of the bridge that will come from the superstructure, and for the steel plate girder bridge, most of the weight that will come from the RC deck. So that's what we want to see, how the forces would flow from the RC deck down to the plate girders, through the shear connectors, through the cross frames, and down to the bearings. The photo that what you see at the bottom right, these are here half scale of the towers of a segment of the towers of the Bay Bridge. And what we wanted to see, what will be the behavior of the links between the two towers. These are what we call them shear links, and they are actually intentionally designed to yield during seismic event so that we will be able to dissipate the input motion of the earthquake. This is here another photo that we have on the shake table. And this is what you see, a curved bridge. And that's what we wanted to see, what will be the behavior of a curved bridge and what is the behavior of a skew bridge, so that we'll be able to understand how the forces would flow in a system level. So all of these things that we have worked on and the work has been used in the field. The photo on the right, these are the towers of the Richmond Sarafal Bridge, and that's where we have the shear links between the eccentric braces. The photo in the middle, these are part of the tower of the Bay Bridge, and in between is the shear link, the one that what I showed you before. The photo on the left, these are the perforated plates that we have used them on the San Francisco Oakland Bay Bridge. So as you see that we work with the engineers, and we work with the code development, so that we will be able to put all the results that what we have learned, so that we'll be able to use the photo or the slide or the writing that what you see at the bottom of the page. This is here from the AASHTO specification. This is here inside the steel section, 16.6.16, and that will give you the provisions for the seismic design. And that's what I wrote for the AASHTO. That will be able to involve what is mainly the load path for steel plate girder bridges, and that's what we're gonna touch on during the talk today. So the first thing, when you look at a bridge, it will give you the impression that they are a simple structure. That's actually not the case. These are really complicated structure because of the geometrical shape of the bridge. Most of the mass is really in the deck, and based on the heights of the column, based on geometrical shape of the bridge, if it was skew or if it was curved, that will give you a very complex behavior. Recent earthquakes that have really showed us that the highway bridges did not behave well, and we need to really better understand why, and we need to really understand how we will be able to improve on that design. For the poor performance, it was really attributed to the design philosophy, and with the second thing, with the attention to the details. So these two things are extremely important, is that what is the design that what you are using, and what is the detail that what you are really providing. We have learned that the collapse was really based on the discontinuity of the superstructure and the lack of for the redundancy of the bridge, because it's really unlike a multi-story building. You have a very high redundant structure, but for a bridge you don't have that one as much as the redundancy that what you see in a building. So the basic response of the bridge during the earthquake load, the earthquake load is a dynamic force, so it's really generated by the mass, and the force will be equal mass times the acceleration, and the mass will be equal W over G, and it will be taken as the weight multiplied by the A over G. The A over G, or the A, this is here where most of the work has been done. So if you go to the AASHTO specification, this is where you see that this A will become so many factors to be able to know how to be able to see what is the seismic force on the bridge. So lots of effort used to be able to estimate A, and that's what you see inside the building code or the bridge code. The bottom line is that what will be the estimate of the A, and how we can include the redundancy, how we can include the importance of the bridge, and how we can include the other factors that will go within the seismic design. The forces will flow through the various components of the bridge, and that will be the load path. And that is extremely important, because once the forces would flow, we need to allow that, because they will cause deformations. And if we didn't detail well, that will be able to have the cause of a failure. Or if we did not provide seat width to be able the structure to slide on for the movement, this is when you have the unseating of the superstructure. So these are the main four things that what we have to pay attention to. Is that the first one is the inadequate seismic load path. If you don't have a clear and also fully designed the component for the seismic load path, you're going to have a failure of the components, and you might have a collapse of the bridge. The second part is that the unseating of the span during the insufficient the support length. The third one is that, as I told you before, the mass is in the superstructure. It needs to go down to the column. And if you did not design the column one for the flexure or for shear during to detailing, for the ductility, for the flexure, or if you don't have the adequate reinforcement, lateral reinforcement for shear, you will have a failure on that part. And then you will see a damage at the expansion joint, and what you see a damage at the support locations, because this is where you tend to collect all the seismic forces down from the superstructure to the substructure. So I'm going to show you a list of photos here, and keep in mind that what will be the cause of the collapse of here is that this is here at the abutment. This is a seat type abutment. And the main cause of that one is the short support length. So that means that we need to provide an adequate seat at the abutment so that the superstructure could slide without unseating of the superstructure. These are the same thing, very short seat width for a concrete bridge, and the same thing for a steel bridge. So the support length, allowing movement at the support locations, if you have a discontinuity, is extremely important. This is here what's called the expansion joint. And we used to do that to be able to allow the superstructure to move, to take down the temperature loading on the column. And for the temperature loading, you need to allow very short movement. For that one is really adequate for the temperature loading, but for the seismic forces, as you may expect, these are very short for the seismic forces, and they tend to unseat for that part. This is the same thing. It's expansion joint, and that will show you the unseating of the superstructure at the expansion joint. This is the same thing for a steel bridge, and that's what you see, that the top of the bent cap, and you see the steel plate girder bridge wanted to move, and these things will become part of the seismic load path. And as you see here, if you look very carefully here, you see that where are the anchor rods, and you see that the lack of reinforcement of that will surround the anchor rods, and that have failed. If the earthquake was actually bigger a little bit, that will cause the unseating of the, for the plate girder. This is here a close-up, and that will show you the lack of details at for the reinforcement at the anchor rods. This is here at the abutment. It's the same thing. Same thing for a steel plate girder bridge, as you see that the differential movement between the superstructure and the bent cap. This is here damage at the support location. As I told you before, for a steel plate girder bridge, it has many components. You have the deck. This is where most of the mass is. And then you have the plate girders. So the forces would go from the deck to the plate girders through the shear connectors, or what's called the shear studs. And from that, it will go to the cross frames. From the cross frames, it will go to the bearings. So here you will see a damage at the plate girder. This damage is caused from the forces that they are in the cross frames. So as you see that the location of the cross frames, this is a straight bridge, by the way. And for a straight bridge, most of the time, the cross frames, they are really secondary members for the gravity load. But for seismic load, the cross frames at the support locations will become primary members, as we have inside the AASHTO specifications. More details at the support locations. This is here the Old Bay Bridge. This is the eastern span. And this is here failure of the panel due to short support length. These are two structures, the one to the right and the one to the left. They have moved apart during the earthquake, and that caused the panel at this expansion to drop. So seat width, support length is extremely important when you allow movement for the bridge. This is here a column, what you are looking at, the reinforcement. This is here number 18 bars. These are the biggest bars that what you may think of. And this is here show you that the lack of the anchorage to the footing. So it will show you the slippage of the reinforcement because of the construction method at that time. You will have what's called dowel bars. These go from the footing, and then we will use a splice. We will use a lap splice from the reinforcement that will go on the footing to the column, and during the earthquake, the lap splice would actually slip, and that will cause the failure, and that will cause this type of a behavior. So the development length will be extremely important to allow the connection between the column down to the footing, and the same thing to the bent cap or the cap beam. This is a skew bridge, and as you may expect for a skew bridge, you will have torsion, and the torsion will cause shear, and these are the failure of the reinforcement due to the lack of confinement and due to the lack of the lateral steel that will resist the shear. So as you see that the geometrical part of the superstructure, if it was curved or it was skew, it will play a very important role on the detailing of the column. All of these things, this is here inside the cypress, actually viaduct, and that will show you the lack of the confinement steel, the lack of lateral steel, and the lack of joint shear reinforcement. This is here a double deck, it pancaked, and you will see that what will be the effect of a failure of the columns on that. This is here a shear failure of the double deck at a different location. These are failure at the end of the column. As you will see here, there was a channel, and they have changed the detail of the reinforcement. So what you need to expect that if there is a change in the details and there is a change in the boundary condition, you need to pay attention and make sure that the reinforcement is not only for the confinement at the end of the column, because here they have changed the location where is the end of the column and where is the footing is. More of the lack of the confinement for the longitudinal bars, because once you have the failure of the lateral steel, you will have the buckling of the longitudinal bars, as you see from these two photos. That's a joint shear failure. That's here, it's the effect of the flare. As you may know that when we have a column, we like to flare it in the transverse direction so that we'll be able to cut on the bending moment inside the bend cap. So that's why we mainly flare the column in the transverse direction. So the flare would make, the flare will have an effect on where is the location of the plastic hinge, so that will shift the location of the plastic hinge from the top of the column to the location that where you see here. And based on that one, this is a very short column, so the shear will become very high, and with the lack of the lateral reinforcement, you will tend to see that the buckling of the longitudinal bars. This is here for a steel bridge, and that will show you the location of steel restrainers inside the longitudinal direction, and you see the buckling of the restrainers. We talked about very briefly about the steel plate girder bridge. This is here the cross frames between the plate girders. As I told you before, as part of at the location of the support, the cross frames will become primary members for seismic forces, and they will be able, they need to transfer the seismic forces from the deck, from the plate girders down to the bearings. And if you don't design them well, as you see here, they do tend to yield or buckle or even to fracture if they are not detailed well based on B/T ratio and local buckling effect. So these are the main 4 lessons that we have learned. And if you're gonna take away from my talk this, today, is that the most important thing is the support length. It's the unseating of the superstructure at expansion joint. The second one is the slippage of the main reinforcement. That's why we don't allow lap splices. That's why we need to pay attention to development length. The third one is the crushing of the concrete, and that's why we need to have a confinement steel, lateral steel for the confinement. The fourth one is the failure in shear inside reinforced concrete column, and shear inside concrete column that will happen. That will be brittle, and that's what you want to have lateral reinforcement for the shear resistance based on a plastic hinging of the column. So that's what you want to really calculate. What is the force that will come from the plastic hinging if you have a plastic hinge at the top and the bottom of the column, and you have to amplify that to be able to design it to take the shear inside the column so that it wouldn't be the weak link. So these are the main 4 things that what you have to pay attention to as a designer, and that's what you want to provide details. So as you hear me, more and more details will become extremely important for your design. So details, designing well, and also constructing well with inspection. Make sure that the construction is the same thing as your design reflect. That will become extremely important for a good behavior of the bridge. One of the basic questions that what we have once we have the 71 earthquake is that, can we design a bridge to respond elastically for the biggest earthquake? The answer is yes, but it's really not economically. Because if you are dealing with a box girder with integral cap and a seat-type abutment, if you want to design it inside the elastic range, you will get into a loop that the column will become bigger each time that what you want to iterate on the design. And when the column will become bigger, the footing will become also bigger, the superstructure size will become larger, and that's what you will get into a vicious cycle, that what you will get a very large size for the column for that, and it will become really not realistic to be able to do that. So the answer is that we need to allow the reinforced concrete column to yield during the seismic event, so that to really lower the seismic forces and to limit them to the ultimate capacity, so that regardless how big is the earthquake, the maximum force will be the same, right? However, for the bigger earthquake, even though that you have the limit on the maximum force, the displacement will become larger. So please pay attention that even if you do a ductile design of a column and a ductile design of the bridge based on yielding of the column, doesn't mean that the biggest earthquake will not damage the bridge, even though that the seismic force is really limited by the capacity of the column, but for the bigger earthquake will cause bigger deformation. So detailing will become extremely important. That's why we need to really provide the adequate seat width at expansion joints and at the abutments. So that's how we learn. We learn from the damage to the bridge, and then after the damage, as I told you before, we go and we do investigate what happened, and then we reflect on what was the code at that time and what things that we need to change, and we change the code, and we either wait for the earthquake, for the next earthquake to come, or we do experimental testing inside the lab, and we will be able to see how these new details would behave, and we will change the construction. So as you see that this is here a cycle, and it will really never end until that we really perfect, quote unquote perfect, the design of and the design and the detail of the bridge. So these are the list of the timeline of the AASHTO specification. There is no need for me to go through this. So as I told you before, the seismic force, it's a weight multiplied by some factor. And pre the 73, that was 2 to 6%. And that's what we have designed most of the long span bridges based on the weight of the bridge, 2 to 6%. If you look at this factor now, we are talking about 2 times or 3 times sometimes the weight. So as you see that there is a big difference between what was the bridges designed at that time and what is the current design code would actually require. Most of the highway bridges in the US was actually designed in the 60s, and also the 70s. So as you may expect, we have many bridges that they are in use that they are really designed to a lower seismic forces. And that's why we need to do an upgrade or what's called a retrofit for these bridges. So you have to worry about what you have on the existing highway system, and you have also to worry about on the new design so that you will use the right seismic forces in terms of strength and in terms of details. You could really map out here the changes in the code and inside the specification based on the earthquake, based on the San Fernando earthquake, based on Loma Prieta earthquake, and based on Northridge earthquake. So as you see here, the latest is the AASHTO LRFD, and that will be a force-based. And for the AASHTO guide specs, this is a displacement-based. So you have two design methods. You have a force-based and you have a displacement-based. You may want to ask yourself is that which one is the best to use? The answer is that both of them are the same. Both of them will give you the same performance. You don't get a better bridge if you design it based on the seismic on the guide specs, or you don't get a better bridge if you design it on the main specs for the LRFD. You will get the same because the force-based, we have implied, we force you how to do a detail without really telling you what you are doing there in terms of an implicit way. We have implied details for the reinforcement, for the support length, and for the confinement, so that we will be able to take what level of ductility you need. So the basic answer is that if you design the bridge based on the main specs, which is a force base, or based on the guide specs, which is displacement based, you will get the same for the same performance. You are the designer and you really control the seismic response of the bridge. You need to understand that. Based on your design and based on your details, you will control how that bridge would really respond during the earthquake. You have a seismic performance objective. For the AASHTO specification, the performance objective mainly is life safety. So you will expect that the bridge may be actually damaged, severely damaged, but there's no collapse. So that will be the performance objective. This is extremely important, is that what you want from the bridge after the earthquake. We are not talking about serviceability. We are not talking about limited damage. We are talking about significant damage with the main cause is that life safety. There is no collapse. It depends on so many things to be able to achieve that. It depends on the computational models. It depends on the analysis. For the sake of time, today we are not really covering the computational models for a bridge or the analysis. We are really focusing on the design and also details. So if you look at the response of the bridge in the longitudinal direction, as you will see that at the end, if you have a C-type abutment, you need to allow the displacement at that location because you have the elastomeric bearing pads at the end of the bridge and they tend to slide and you want to allow the bridge to slide. If you don't have the ample seat width, you will unseat the bridge or you will damage the abutment. That's why for the back wall, we actually detail it so that it will fail during the longitudinal motion so that we don't damage the piles of the abutment, so that after the earthquake, we can come back and use the same abutment, fix the back wall, and take care of that detail. The second part is that you need to look at how we are connecting for the superstructure to the column itself. You have there a bent cap, and the bent cap could be of two things. Could be a dropped cap or could be an integral cap. Most of the California construction, it will be an integral cap. It will be monolithic. If you have a box girder, the bent cap will be inside the box. You tend not to see it. The column would go frame inside the bent cap. And if you have a steel plate girder bridge, most of the time you will see a dropped cap. And what you need to have a bearing and what you need to have shear keys for that one. So details of these will be able to dictate what will be the design and the bending moment that what you see. The photo of on the top, the cartoon at the top, you will see that this is here an integral cap. You will see at the top of the column to the cap, you will see a rigid, but you will see a rigid connection. And at the bottom, you will see a fixity. So for the bending moment, as you will see here, you will have a double curvature. And that will be very important, as I told you before, for the shear, because it will give you 2 MP divided by the column height. While if you have a dropped cap, you need to worry about how the forces would go from the superstructure to the bent cap. And that's where you need to think about if you have a bearing or if you want to have shear keys in the longitudinal direction so that to transfer the force from the superstructure down to the bent cap. And that, as you will see here, that will be a single curvature. And that will have an important implication on what will be the shear on the column. So that will give you 1 MP divided by L because of the moment that will happen at the base of the column. So the integral cap or the dropped cap will have a very important implication on the stiffness of the bridge, and because if you have an integral cap, you will have a stiffer bridge. And if you have a dropped cap, you will have less stiff and you will have a single curvature type. So both of them are fine. It depends on how you are detailing things. For the integral cap, make sure that once you have an integral cap, and as I told you before, you have a bending moment at the top of the column, this bending moment at the top of the column would really transfer to the moment inside the superstructure. So based on this mechanism here, if you want to be able to see that, you will have forces, seismic forces, at the end of the bridge where the bearing is, and one of them will be actually compression force, and the second one will be a tension force. So that will be an uplift that will be able to show you that the bridge, if it's not really heavy enough, it will uplift. Once you will have the uplift, this here bending moment that what we show on the superstructure on the left side cannot really materialize because you cannot restrain the bridge from that, and all the moment of the column would go to the right hand side. So please pay attention to these things. Once you do free body diagram and sketches that what you do from basic statics will become extremely important regardless whatever the computer program would actually show you. So these things you need to add them up to the earthquake force or to subtract it, and that's what you have to pay attention to once you want to design the superstructure for the seismic load. Load path in a steel plate girder bridge, as you will see here, as I told you before, you will have the RC deck. You will have a composite construction. So the forces would go from the RC deck to the shear connectors or shear studs, and then from the shear connectors, the shear studs will go to the plate girder. Please pay attention to There are people that they are really concerned of the fatigue at the negative moment for the superstructure, so they tend not to put shear connectors there because of the worry about the welding on the top flange of a plate girder. So they will tend not to put any shear connectors. And that will really defy how the seismic forces would go to the band. So if you do that, you will have what's called a lateral torsional buckling on the plate girders, and you wouldn't be able to really transfer the forces down to the column. So as you hear me before, details are extremely important. So we need to provide shear connectors at the location of the support, where is the bend cap, where you have a negative moment from the dead load, and you design it for the fatigue, you check it for the fatigue for the plate girder itself. And also the cross frames at the support locations will become primary members. And you want to make sure that to design them for the seismic forces, if you want to have them to stay inside the elastic range, or as you will see later on, you could allow them to yield and to buckle so that they will be able to dissipate the seismic forces. Bearings and shear keys will become extremely important. So these are basic concepts. What we want to call capacity protected. That means that you will limit the damage to the selected elements. The damage will be controlled and also limited to a ductile element. Ductile element and the reinforced concrete means that you have confinement. You don't want to have the crushing of the concrete or to delay it. You don't want to have the buckling of the longitudinal bars. For steel, you have to pay attention to B over T ratio, compactness. You have to also pay attention on KL over R. So these are extremely important to be able to have a ductile design. The damage, what you want to be able to see the damage so that you will inspect it and you want to repair it after the earthquake. All the rest, besides these ductile elements, you could actually design them to stay inside the elastic range, and that will be the capacity protected concept. Why we need to do that? Because we can limit the internal forces to the ultimate capacity of the plastic mechanism at that element. That one, regardless of the earthquake shaking. Pay attention that, as I told you before, if you have a larger earthquake, even though that the force is the same, but you will have a larger deformation. That's a very important thing. So does not mean that you have a plastic hinge, you have really limited the seismic forces. Indeed you did, but you may have larger deformations due to the bigger earthquake. So that will give you the concept of the yielding and of the elastic response. And if you pay attention here at delta yi, and that will give you where is the force Fp, the plastic force, and where you see the elastic force at the delta P. And based on this one, very roughly, if you take the ratio of the FQ divided by FP, that will give you an R factor, which is a response modification factor that we normally use it in a force displacement design. This is here where you see the seismic forces and where you see the limit on the seismic forces regardless where is the inertia force, because it will be the V sub P will be the plastic shear on the column regardless what will be the inertia force, or regardless what will be the ground motion. So that limit is V sub P, but regardless what will be the earthquake, what will be the magnitude of the earthquake. But as I said before, bigger earthquakes will be able to give you larger displacement. This is here some series of the tests that we did on a steel plate girder bridge on the superstructure. I want you to pay attention. I don't know if you can see my cursor or not. I want you to pay attention to the end. These are the cross frames. As I told you before, if we allow them to buckle or yield, that will be ductile element. If we don't allow them, that will be an elastic. And if we use a buckling restraint brace, that will be a BRB. That means that we are forcing the brace to yield under the compression. Once you push a force, the steel bar inside the casing here will become like a snake, and that will actually yield instead of a buckle, and that will give you the yielding of the BRB. So here, based on these things, you will see that I was able, to limit for the lateral force. As you see here, is that regardless how much we are pushing, there is a limit on the lateral force. But as I told you before, there is a larger displacement. This is here for the single angle. These are designed as a ductile, means that we have taken care of the B over T, and we have taken care of the slenderness ratio. This is here for the BRB, and if we compare what will be the base shear to the weight of the bridge, for the elastic response is 1.24, and the displacement is 0.21. For a ductile, based on the angles, we were able to reduce what will be the lateral force, but we have a larger displacement. BRB is the same thing. We have reduced the force, and we have a lesser displacement. So the lateral force, once you have a yielding element, you will limit what will be the base shear, but you will have a larger displacement. And that's what you want to make sure that you are allowing for this kind of a displacement. Let's talk about what will be for the seismic performance, the criteria. According to AASHTO, we are designing for life safety. So that means that we are not designing for the serviceability or for limited damage of the bridge. We really worry about life safety. We design for a seismic hazard, as I'm going to talk about later on, for a 7% of exceedance in 75 years. Why 75 years? This is the AASHTO defined lifespan of a bridge. That's how they have actually decided it will be 75 years. You will have a low probability of collapse. There is no zero collapse. It's a low probability. You will have a significant damage and a disruption to services. Services here, we are talking about traffic. You will have a partial, or you need to have a complete replacement of the bridge. So that's what you are doing. You are designing for life safety. Make sure that we don't have people die on the bridge or actually underneath the bridge. That's the main thing. But we don't really worry about what we need from the bridge after that. What you want to really pay attention about the earthquake resisting system, what's called the ERS, that will give you a load path. And the word is extremely important, uninterrupted load path. If you have an interrupted load path, you will have a collapse. So what you are talking about, uninterrupted load path. You can really dissipate the energy through a yielding mechanism to be able to control the seismic displacement. And for the essential elements of the earthquake resisting for the resisting system are three. The first one is really simplicity. You want to know how is the clear load path. That's why it's extremely important to sketch the shear force and the bending moment diagram by hand, so that regardless what a computer program you are using, it's extremely important to sketch how the forces are and follow the forces where they go. So actually simple statics would give you a lot of behavior of the bridge. You want to have an integrity. That means that you want to have an adequate connection. If it was integral connection, or if it was not, you need to know how the forces would flow from one element to the other one. You want to have the symmetry as much as you can. We are talking about a balance in the stiffness. The length of the columns will become extremely important. If you can have them the same length rather than to have a short actually columns at the end of the bridge, we tend to have short columns according to the profile of the ground. That will give you a change in the stiffness, change in mass, change in strength. That will give you an asymmetric, and that will be the cause of a different response of the bridge. We have three types of the design strategies. The most actually common one is type 1, which is a ductile substructure with essentially elastic superstructure. Type 2, this is mainly for a steel plate girder bridge. As I told you, that we can allow the yielding and the buckling of the cross frames, and that's what we call essentially elastic substructure with a ductile superstructure. Type 3, this is here when you have a fusing mechanism between the superstructure and the substructure, and that's what's really base isolation is. So that will give you here a response of the longitudinal direction of the bridge. That will show you where is the location of the plastic hinge. We will have, this is type 1, for the superstructure, it is in the elastic range. And for the substructure, this is where you have the plastic hinging. This is where you see the plastic hinging at the top of the column, underneath the bend cap, or at the top of the footing, or at the top of the pile shaft. And this is where you want to detail that location so that you will be able to allow the formation of a plastic hinge. This one here, it will show you a full-scale column, and it was actually cycled back and forth, and that will show you what is the location of a plastic hinge. For that one, normally it's 3D inside the ground. 3D is the diameter of the column. It will range between 2.5 to 3D, and that will be the location where you have the plastic hinge. This is a very important photo. That for this photo, what you will be able to see the effect of the confinement. Once you lose the lateral steel, you will have the crushing of the bars of the concrete, and you will have the buckling of the longitudinal bars. So these are the sequence of the event. You will have the failure of the lateral steel, and you will have the crushing of the concrete, and you will have the buckling of the longitudinal bars, and that will be the end of the yielding mechanism. You could use the abutment to be able to take some of the force, as I told you before. And this one here, it will show you that the back wall at this location, we like to fuse it so that it will fail during the seismic event, and so that to protect the piles underneath, so we can reuse the abutment and its piles after the earthquake. These are the locations of the plastic hinging inside for the superstructure. We need to pay attention to that, or here inside the bend cap, we need to pay attention to this. if we're gonna allow that thing to happen. This is here type 3. This is where you have base isolation between the, it's a fusing mechanism between the superstructure and the substructure. As I told you before, details are important. As you see here, this is an expansion joint. And instead of having one side of the superstructure would sit on the other side, we have actually provided 2 columns. And as you see that even if we have movement of the 2 frames here, we will be able, we don't see the unseating of the superstructure. This is here where we had extended the length of the column here inside the footing to allow the same, for the same actually column height between all the locations of the column. This is here type 2, where we will allow the plastic hinge, where we will allow the yielding inside the cross frames, and where you see here that you need to detail these things as for the B/T ratio and for the KL over R. Please pay attention that what will be the forces that will come from the deck to the shear connectors, from the shear connectors to the cross frames, from the cross frames down to the bearing. So as I told you before, free body diagrams and simple statics will be able to help you how the forces would flow from one element to the other. So here I have some of the videos. Unfortunately, you cannot hear the sound. So that one, it will show you a plate girder. So as you see here, this is here the plate girder. The forces would go from the deck, from the plate girder to the cross frames, through the bearing, down to the bent cap. This is here how the cap would actually behave underneath. So here what you are seeing is actually series of motions that will go up to 200% of the design level earthquakes. This one here, what you see at the abutment, so please pay attention and I will show you a close up. So here what you want to pay attention, what will be the motion and the displacement at the abutment and also the uplift of the plate girders. So here from underneath of the bridge, notice the uplift. So you could see the uplift, the one that what I talked about before. So these are how the forces would go in the transverse direction. This is what's called shear keys. These are the transverse shear keys, and that's what you would like them to fail at a specified level so that what you will be able to really protect the piles at the abutment as I talked about it before. So now I want to switch and talk about the seismic hazard. And what do you mean by the seismic hazard of a site? The seismic hazard is the hazard will be associated with the earthquake at a particular area, and it will give you what will be the intensity of the ground motion at the site. And we need to amplify that from the rock to be able to see what will be the effect of the soil for that site. These are the locations of the earthquakes throughout the world. As you will see that these are based on the plate tectonics, and you will see that where are the locations. These are the epicenters of all of the earthquakes from the 63 till 1998. And in 2007, what actually AASHTO adopted a 1,000-year return event. And these are, as I told you before, 7% of the probability of exceedance. They gave actually hazard maps to be able to really estimate the location of the earthquake. And here is the equation that will be able to give you the probability of exceedance, and that will give you the return period throughout the years, so that if you plug in the 7% and 75 years, you will get a 1,000-year the return period. So what you have, if you go through the AASHTO specs, they will give you 4 maps, and the 4 maps, they will give you which is called the design earthquake. They will give you the PGA, this is PA. They will give you for the S sub S, this is for the short. And this was here for the S sub 1 for the 1 second that will give you the acceleration for that. Based on these, you would be able to get the seismic coefficient spectra and make sure that this is not the acceleration spectra. This is the seismic coefficient spectra. This is what AASHTO actually call it. So as I said, it's not the acceleration response, the spectrum. This is the seismic coefficient spectrum. So these are the maps, and what you want to account for the site to modify them to be able to account for the local sites. And why we need to do that, this is here what we have measured. The horizontal axis is the period, and the vertical axis is the spectral acceleration. This is what was the bedrock acceleration, and this is here where we have seen that the effect of the soil. This is here soft inside Oakland, and this is here soft soil inside the south of San Francisco. So you will see that how much will be the amplification of the motion due to the site effect. So these are the site classes we have from A to F, and once you are in F, or what you want to have a specific thing, what you want to hire a geotechnical engineer to be able to help you with that site. And most of the time we use actually between C and D, and that will give you the values to be able to account for the site factor. So we have these values for the FPGA, and where we have the F sub A, this is the acceleration, and this is for V for the velocity. We will be able to get S sub ds, and we will be able to get S sub d1, and these are the anchor points for the acceleration spectrum or for the site response spectrum. So here, this is the coefficient, the spectrum for the elastic design. This is here the PGA multiplied by the FPGA. This is here the F sub A times the S sub S. This is at T sub 0, which is equal 0.2 times T sub S. where T sub S will be equal S sub D1 over divided by the F sub ds. This is here the descending branch. We divide by T to the power of 1. So this is a decay motion. And if we need to continue that, there will be a different spectrum, and that will become important for the base isolation. So this one here, it will show you the spectrum here for Los Angeles. And as you will see that if you have a bridge of period 0.5 seconds, you are having very close to 1.8. So you need to take the weight of the bridge multiplied by almost 1.8. That will give you the seismic force. What is the importance of the acceleration coefficient for the S sub D1? It will give you what are the seismic zones. We have 4 seismic zones. If you are in a high seismic area, most of the time you will be in seismic zone 4. What does it mean? It will dictate on you the analysis method. It will dictate on you what will be the support length. It will also dictate on you what will be the column detail and what will be the foundation and the abutment design procedure. So as I told you before, we have 2 design methods. We have the force-based and we have the displacement-based. Both of them, as I said before, would give you the same for the same objective, which is the collapse, the prevention of the collapse. Both methods will give you ductility inside the columns, inside the load path, to be able to resist the earthquake loads. In the force-based, we need to, this is inside the main, for the main AASHTO specs, we need to have the seismic demand forces for the yielding element, so that you will do the elastic analysis and make sure that when you do the elastic analysis, we have to use the cracked eye of the column from a curvature analysis or from some other means that you will be able to get what will be the cracked eye. And then for that element that what you want to design as a yielding element, you will divide the forces by the appropriate, the R factor, which is called the response modification factor. You need to provide details for that, and we have implied details. We don't tell you how you are doing that, but we tell you what will be the minimum confinement steel, the minimum reinforcement, all of these things that you will be able to really guarantee what will be the ductile behavior of that element. You need to provide also an adequate load path, and you need to provide displacements for the other locations of the bridge. So based on the AASHTO specification, we have what's called the categories for the operational categories, and we have the critical, we have essential, and we have the other. The critical, it is for 3% of 2,500 years. This is here for what we do. For example, if we want to design the Bay Bridge, that will be a critical structure. And what we want to have the bridge essentially elastic. This one here is if we want to have only operational for the emergency vehicles. The third one, which is called the other, and that's what we normally design. Most of the highway bridges, we design them under the other. What will be the difference in these? That will be the R factors. So here is the response modification factor for the substructure. So as you can see, we have three categories: the critical, the essential, and the other. the critical, as you see here, all of these are 1.5. So if you want to really design the bridge to stay inside the elastic range, it will be 1. But if you want to have it essentially elastic, you will use as 1.5, and that will ensure that the bridge will be operational after the earthquake, and you have an elastic design. And this is where you have the other, and this is where you see the R factor equal to 5 or equal to 3. And I told you before where the R factors come. It will come from the displacement ductility, and that's what you want to really provide. We have put inside the code implied things for the confinement steel, for the lateral reinforcement, to make sure that the bridge to make sure that a ductile behavior for that element. Look at the connections here. As you will see that for the superstructure to the abutment and for the expansion joint within the superstructure, we have it 0.8. So that means that we are amplifying the elastic seismic forces, because what we would like to keep all of these things inside the elastic range. So this one here is a reduction for ductile element. For the elastic design, it's like a capacity protected implied, and that's how we are changing the R factor to be able to do that. So you are amplifying the elastic forces at the abutment and at the expansion joint, because these are extremely important for the unseating of the superstructure. While we have the displacement method, what we want to really provide a yielding system to ensure that the demand displacement less than the displacement capacity of the yielding element. So here we ask you to do more detailed type of a design. You need to do a curvature analysis for the concrete, so that you will be able to estimate what will be the ultimate curvature. You need to know what will be the length of the plastic hinge. You want to know what will be the ultimate displacement of the element, and what you want to make sure that the ultimate displacement is really more than the demand displacement, so that what you will have a safe design. So here it's more detailed and more behavior, so that you will be able to know what is the behavior of the concrete element or the steel element, and you need to provide for the other element what you want to provide an adequate strength. So locate where is the yielding element, do what you need in terms of to really determine what will be the capacity of the yielding element, and then design the rest so that they will stay inside the elastic range to the ultimate capacity of the yielding element. So as I told you before, is that no one is really better than the other one. Both of them are the same. Both of them, they will give you the similar performance. For the R factor, these are really prescribed for the first base, and you will use them to size the yielding element. You don't need to do any verification of the actual displacement of the ductility demand, because we gave you prescribed detailing for these elements. For the displacement-based method, it is a displacement capacity of the yielding element. You have to evaluate it. You have also to compare it to the displacement demand, and you have to detail it so that you will be able to get what is the required displacement. So these are the elements of the capacity design. You have to select where the location of the damage or the yielding what you want to have. Keep in mind that I told you about 3 types: type 1, type 2, type 3, and they will tell you where the damage that what you would like it to be. So based on that, you will design these elements to be ductile. Ductile for the reinforced concrete, to prevent the crushing of the concrete or the buckling of the longitudinal bars. You have to really delay that. And then based on these things, you have to protect. You have to protect all the other elements. So these are the three things. What you have to select, design, and also protect. The select, what you will get it from type 1, type 2, type 3. Based on the selection, you will design the element to be a ductile element. And then all the rest, you have to protect them. What you have to use the ultimate capacity of the yielding element multiplied by some factor so that you will be able to ensure that these elements will stay inside the elastic range. So this is the basic concept of the capacity protection. So imagine that what you have a chain and you have selected that the yielding element will be in the middle of that chain. So that once you have the yielding element, that means that you are really here is that limiting the forces to the force inside the ductile link, which is equal to F sub D. There is no way to exceed that. But what you want to make sure that this element can really displace at the displacement needed so that you don't want to fracture that. So that will be the capacity protection design. What are the elements that what you have to do the protection for? Is the column shear, joint shear as the footing, and the bend cap, the footing itself, and the superstructure. So these are the steps for the seismic design. The first one is that what you want to determine what will be the seismic input, what you want to find what will be the seismic hazard, the site. For the site classification, you have to get the spectrum for that site. You have to establish what will be the seismic zone, because as I told you before, the importance of the seismic zone dictate many things. What will be the analysis method that what you have to use, dictate what will be the detailing, what will be the level of the support length, all of these. Importance of the bridge, the analysis, how you are modeling for the foundations. You have to identify the earthquake resisting the system and what will be the design strategy, type 1, type 2, or type 3. And if you want to, what will be the yielding, what will be the deformation, and if you want to have the participation of the abutments or not. And based on these things, you will do a demand analysis. You have to do a bridge modeling to do for the analysis method, linear, nonlinear, and so forth. And then what you have to do, the design and check the earthquake resisting element. You could use a force-based or you could use a displacement-based. You will do a detailed ductile element for the design. You have to do a capacity protection, the shear, the bend caps, the shear inside the columns, the bend caps, the foundation and the footings, and for the superstructure connections and the bearing. So here to wrap up, we have talked about what is the design code, and we have talked about what will be the design methods. We have actually talked about is the design code is based on life safety. And we have talked about the load path, the importance of the seismic load path. We have talked about the importance of all the elements inside the seismic load path. We have talked about two design codes. One is the main code, the LRFD, seismic design, the LRFD design specification, and the guide specs. The main specs, which is the LRFD design specification, that will give you a force-based. You will have an R factor there. You will have values for the R factor. You will have values for the yielding element where the R factor is more than 1. For the protected element, you have the R factor equal to 1 or actually less than 1. That will become an amplification factor. We have the guide specs for the seismic design. That will be displacement based. You need to do more detailed design and more detailed the analysis for the concrete and for the steel, the curvature analysis, and all of these to make sure that the displacement actual capacity less than the demand displacement. And we talked about what are the steps of the design. You have to select, you have to design, and you have to protect. So these are the main elements that what we have. And I will turn it over now to Bodhi to see what he wants to do. We are very close to 1 hour 22. If he wants to take a break or if he wants to allow for some questions so that we will have till 7:30 my time. Bodhi?
So Dr. Itani, we don't have a lot of questions right now. So maybe at the end, they will ask questions like all the attendees. So we can take a break now for 5 minutes and then Dr. Saiidi will continue, right?
Okay, very good. Thank you.
Yeah. Okay. Okay. Thank you.
Okay, Bodhi, should I put my screen on right now?
Yeah.
Okay, I'm putting the share button here. Am I allowed to do that now?
Oh, right. Just a second. I have to give you the privilege. Yeah. Now you can share your screen. Yeah.
Okay. See my screen now?
Yeah, I do.
This is the
so you have to go to the slideshow mode.
It's not presentation mode yet. Let me go to okay.
Yes, perfect.
Okay. This is full screen now. Do you see full screen?
It is full screen, right?
All right, great. So we are ready to go whenever the break is over. So I'll wait to hear from you.
So, so we'll start at 9:30 and then continue, right?
Sure, it's just up to you. If you want to take a break for a few minutes, that's fine. If you want me to just go ahead, start it, and have more time for Q&A at the end, we can do that too. So it's up to you.
Yeah, let's take a couple of minutes break and then we'll start.
We'll take a couple of minutes of break. That's fine.
Yeah.
Okay.
Okay, Dr. Saiidi. So we can start now.
We can start. Okay.
Yeah.
Sounds good. All right. Greetings, everyone. It's a real pleasure to be here. This is Saiidi, distinguished researcher at the UCLA.
Dr. Saiidi, we don't see your slides.
Oh, you don't?
Yeah.
I thought you saw that before.
I saw it before. Right now we don't.
No, you don't. Okay, let me see why we are not seeing that. Okay, let me go back to share.
Yeah.
And that.
Yes.
Okay, can you see? You should see this right now.
Yeah, I do. Yeah.
You see right now?
Yeah.
Okay, great. And you see the change of slide right now. Is that correct?
Correct. Yeah, I do see it.
So let me go back to the first slide. My position right now, I am the distinguished researcher at the University of California, Los Angeles, UCLA. Also emeritus professor at the University of Nevada, Reno, and a senior principal the company that deals with infrastructure innovation, registered in the state of Nevada. What I will talk about is, again, related to seismic design of highway bridges with focus on accelerated bridge construction and using innovative materials. And you will see why we are trying to do that. So I will give you a summary of some of the research that was funded by a variety of agencies, including the California Department of Transportation, Federal Highway Administration, NCHRP, the National Science Foundation, Nevada DOT, and Washington Department of Transportation as well. Now, as you can imagine, we are doing our research with the help of many research assistants. So this is a list of research assistants that have been involved in the projects that I will be talking about today. Now, there are 4 topics that I will bring up. The first one is about the next generation of bridge columns. These are the columns that use for accelerated bridge construction. So, which is simply ABC. So you're gonna hear me use the term ABC often during the presentation today. This is a series of projects that were funded by the California Department of Transportation. The second topic is about seismic design of new guidelines that we have developed for AASHTO use. Again, it's for ABC. This one is funded by the National Cooperative Highway Research Program, NCHRP. Seismic resistance of columns that we use carbon fiber reinforced polymer tendons in it. And again, you will see why we're doing that. That was funded by the U.S. Department of Transportation. Also, a completely very new and innovative idea of building bridges that are deconstructible and yet they're able to resist earthquakes with minimum damage. That one was funded by the National Science Foundation. So I will give you a highlight of these projects. Let me start with the next generation of bridge columns for ABC. Well, one of the obvious questions is that what is next generation? What do we mean by that? Here we're talking about prefabricated columns, precast columns, including the type of connections that will be connecting this prefabricated column. But the basic requirements are similar to what Professor Itani talked about in his presentation. They have to meet the seismic performance requirements that he talked about. They obviously have to be constructible, something that relatively easily can be built without complications. And also, they should not introduce unusual issues with respect to maintenance and durability and inspectability of bridges. In the US, we are required to inspect all bridges once every 2 years. So these bridges, whatever we do, they should be something that we can inspect them and assess their condition. Now, the added issues the added considerations are that we want to make these, what makes them next generation is that we want to make them resilient and try to minimize damage. Professor Itani mentioned that the primary goal of current seismic codes for bridges is life safety, or by far the majority of the bridges. Well, we're trying to extend this to also serviceability after earthquake, even for ordinary bridges. Also, in this particular part of my presentation, I'm going to talk about ABC that have connection that conform to the ban on splices. Right now, in the current seismic codes for bridges, splices within plastic hinges are not allowed. And for a variety of reasons, I will discuss that as well. So the question is, how can we do that for this part of my presentation? Now, so there are options to connect prefabricated columns, let's say, to footings here. So in the upper left, you see a precast column that is put into an opening inside the footing. and the space between the two is filled with the grout. It's possible, if you look at the middle picture here, you will see that there's a precast column. However, at the bottom, it has extended bars that are not within the precast column. So these extended bars are placed into an opening into the footing. Then the space is filled with concrete, typically. Or it's possible to have a similar column. If you look at the right side of the image, you will see that there's a precast column with extended bars. However, this time we have put these in grouted ducts. Now, specifically, what I'm going to talk about is that how we can provide connections in these grouted ducts using ultra high performance concrete, or UHPC. Now, you hear about this material on and off, probably. In the US, it's becoming a lot more popular than even 5 years ago. People are seeing its advantages that are being used in a variety of situations in bridges. What makes these ultra high performance material is the special steel fibers that are used, that you see on the left side in the concrete. And if you build a cylinder and cut this cylinder, you're going to see that in the cross section spread throughout the element. And the rest of the ultra high performance concrete is a special grout, and again, they're engineered materials that we are using. What makes this one ultra high performance is that it has a very high compressive strength and tensile ductility. You look at the stress strain diagram under compression on the left side, you see that here you notice that the compressive strength is about 200 megapascal, okay? 200 megapascal compared to, for a good concrete of, we can get about 35, 40 megapascal. So this one is much stronger than ordinary concrete, as you can see. Also, once it begins to fail, you notice that it maintains some level of capacity. In other words, if you look at the purple curve, you notice that after the curve goes down, after it's dropped, we have still about 60 megapascal capacity until we go to relatively large strengths. So this is under compression. Under tension, if you look at the lower figure, you notice that we, at some point, we begin to have a cracking in this, and the capacity is stable. But then we are able to maintain that capacity for relatively higher strengths. In ordinary concrete, as soon as we have a cracking, we have failure. However, the fibers hold the UHPC and allow us to have some level of ductility. Now, this particular project that I'm going to talk about is using this UHPC to anchor precast columns into a footing using grouted ducts, where the ducts are filled with UHPC. This particular part of the study had two segments. One was a study of bond strength itself, and the other one is implementing it in some large-scale columns that tested under cyclic loading that simulate earthquakes. So let's talk about the UHPC testing. Here you notice that we had 14 specimens that were tested. We changed, we had a variety of the parameters here that we played with, including the embedment length, the bar size. We use 25 millimeter bars as well as 36 millimeter bars. Also, we played with the duct size, using 75, 100, or 125 millimeter, different ducts. Also, in a few specimens, we bundle the bars. In some cases, we need to do that in bridge columns. So the question is, if you have bundled bars and you're inserting it in a duct, how's that going to work? Also, we put two ducts in a connection adjacent to each other. See how that works. So The pictures that you see at the bottom, you see the placement of your UHPC. These are again the grouted duct specimens. So you see a single duct in the middle picture here. This is before we placed the UHPC, and the completed specimen, a sample of it is shown on the right side. So we tested these under tension. As you can imagine, in some cases we had the bar pull out, but in some cases we had the entire duct pulling out of the specimen. So you notice that here there are a couple of samples. One has number 8 bars, the other one is number 11 bars, and you notice the entire duct was pulled out. So there are two modes of failure that you could have. One is the bar pulling out from the duct. The other one is the duct itself might pull out. So based on these data, well, first of all, we found that the bond strength of UHPC is about 8 times the bond strength of concrete. So really excellent bond because of the presence of the fiber and special engineered material that we have used in UHPC. So based on this, we developed two equations. One is talks about the pull out of the bar from UHPC, and the other one is the entire duct pulling out. So obviously the anchorage length that we want to provide will go based on the most critical of the two. So we also made comparison of these with the ACI 318 and the Astro LRFT regular grout the duct field, and we find that we can reduce the anchorage length by about 50% because of the high strength of the UHPC in bond. Then we evaluated this in a large-scale column. Actually, there are two column models that we tested. One used conventional steel. The other one we used a smart material, smart reinforcement called shape memory alloy, and we also used ECC. So what you see here is ECC is engineered cementitious composite. We use that in the plastic hinge to minimize damage. But the connection here was through the anchorage of the bars into the ducts that were filled with UHPC. You see the picture on the right side. You see the ducts that were placed into the footing, and the precast column with extended bars, where the bars were placed inside the grout and filled with UHPC. So this is a large-scale column. So the column itself is about 2.7 meter long. This is the column model. So it's a pretty good size, and we're using relatively large bars, the diameter of 25 millimeter. The column itself was 610 millimeter diameter. And the rest of the design was sort of conventional. We designed it to have enough confinement steel. So lateral reinforcement was over 1%. And the axial load that we applied on the column was representative of the type of axial load that we get in bridge columns. So these are some photos of the construction of the column model with the grouted ducts, and again, initially the column was hollow, then we filled it with the self-consolidating concrete. So you notice the placement of the column into the ducts, and then the filling of the ducts with the UHPC. So the column was built, and we tested this under slow cyclic loading. So what you're looking at here is the lateral force versus the drift ratio of the column. Let's concentrate on the one on the left side. On the left side, we had the results for a conventional reinforced concrete column. That one is shown in red. So that's CIP, that's cast in place column. The black one, the black curve on the left side, represents a precast column. Again, conventional material, but precast column, the difference being that the connection was through the grouted ducts. So you notice that we were able to accomplish the strength and pretty much the ductility that we had measured in the cast in place column. The graph on the right side here shows the result for the shape memory alloy. I don't have time to get into much details of that. The idea of shape memory alloy is super elastic, so that what it does, it prevents permanent displacement of the column. So if you look at the right side, the red ones again represent the CIP column or a conventional column. The black curve shows a column that we use UHPC for the connection to the footing in the grouted ducts. But in the plastic hinge, we use that shape memory alloy super elastic material and ECC. And you notice the black curve, the return curve always goes through the origin or near the origin. That means it has very low residual displacement, even though it undergoes large displacement. Nonetheless, you see that the capacity was accomplished the same way that we had for the conventional column. One of the things that is important in the displacement-based design is the pushover curve or the lateral force displacement relationship. So if you compare these, there are three curves here that you see. One is the CIP, that's a conventional reinforced concrete. Nothing new, no precast, nothing. And so that's a red curve. Now, if I look at the one that had conventional material, but it was precast column, but connected to the footing with UHPC in grouted duct, the curve for that one is gray. So you notice practically we had the same kind of behavior in the gray curve and the red curve, the orange curve that you see here. The one that used the shape memory alloy, again, comparable, but we ended up with a lower stiffness. This is because of the lower stiffness of the material that was used, the reinforcing material that was used. The shape memory alloy was made out of nickel titanium that has lower stiffness than steel. Also, the strain hardening characteristics of the material is a little different. That's why you see the dark black curve has a larger strain hardening characteristic. In terms of the observed damage, this is under 5% drift ratio. This would be the maximum credible earthquake that would occur on a bridge typically. And on the left side, you see the column where we use grouted ducts and UHPC in the grouted ducts. If you compare the left side and the one on the right, which was cast in place column, you notice that the damage was quite comparable. In other words, using a precast column with grouted ducts using UHPC provided the same performance, more or less, as cast in place concrete. Now, the one in the middle shows where we use the shape memory alloy and ECC. You notice there is a damage, the damage is lower, there is a concentrated crack, but this is again recentering column. I don't have time to get much into details of that today, but the point of this presentation is what did UHPC filled grouted ducts do for us? And we found that the performance was comparable to what we saw for cast in place concrete. Let me get into topic two. In topic two, I'm going to talk about proposed seismic design guidelines for ABC connections. This was a document that we prepared based on research and studies that we did under the NCHRP, that's National Cooperative Highway Research Program. In this project, we worked with some practicing engineers who did some design examples, as well as they helped with the development of the design guidelines. Now, the report was published less than 2 years ago, so it is available online. It can be downloaded for free. Just to give you an idea about what in this project we have, the table of contents is, well, we did a state-of-the-art review, and there was some experimental testing that we did, as well as extensive analytical work. And then we put everything together and came up with specifications and design examples. And then, of course, there's summary and conclusion. Now, there are a bunch of appendices in this report. We talked about, we did a survey of the state departments of transportation. Then we developed some standard test methods for bar couplers. Now, I'm going to talk about that a little more, see how we can bring these couplers into the design. Now, the previous topic one, I avoided the bar couplers, but in this project, in the NCHRP project, we brought those in and see how we can use them. Then we have the specifications, of course, that we developed, and there are 5 design examples that are included in our work. Now, the big picture, the overall objectives of NCHRP for 105, this is the project that led to this proposed specification, was displacement-based design method for construction and the design of ABC column connections for moderate and high seismic regions. So this was lacking in the designers, even though they want to use ABC, but in high seismic zones and moderate seismic zone, they did not have any guidelines to incorporate this. So that's the purpose of this project, to address that. Now, the type of connections that we included in this project include mechanical bar couplers, the grotted ducts, also pocket and socket type of connections. As I mentioned before, we did experimental work, some testing, as well as analytical work before we developed the guidelines. In my presentation right now, I'm going to focus on the design-related issues, okay? Because I know the audience is designers, and they would be interested in this type of thing. So seismic design of columns with ABC connections, what are the key elements that we have to consider? Also, the bar couplers that have been around for a long time, but they have not been categorized as seismic couplers, we developed standard test methods. What does it take that the manufacturer need to do to prove that, yes, these are appropriate for moderate and high seismic zone applications? And there are, of course, design examples for ABC seismic connections that we show how different details, different connections can be used. Now, one of the major decisions that we made early on was that the ABC design guidelines that we are going to develop will be a supplement will be an appendix to the existing LRFD seismic bridge design. It's a displacement-based design guideline that Professor Itani referred to, but the idea was, rather than developing everything from scratch and repeating a lot of the materials from LRFD seismic design guidelines, we are going to have additional material that will allow an engineer to integrate with this existing guidelines. The provisions that we have developed are about bar couplers, the grotted duct connections, as well as pocket connections. Now, let's talk about couplers. First of all, current seismic codes for bridges do not allow using couplers in plastic hinges. So we are trying to address that. This is, again, when it comes to moderate and high seismic zone, they're banned. Now, there's a variety of couplers that are out there. They have been used for non-seismic applications for a long time to different extents. So the one on the upper left, you see a shear screw coupler. Then we have headed bar couplers. The grotted sleeve coupler is another common popular type of couplers. There are threaded coupler types. There's a variety among them. Also, there is swage couplers that are out there. These are just some of the more common couplers that are available on the market. Now, what is the reason for not allowing couplers in the plastic hinge? There are a couple of reasons. One was the lack of data, actually. There hasn't been much, until, let's say, about 10, 15 years ago, there haven't been much data on seismic performance of bars that are spliced using these mechanical couplers in the plastic hinges. Okay. But other than that, there's also some fundamental reasons why there's some concern about using these couplers. So let's take a look at the figure on the left side. The one on the left side shows a conventional reinforced concrete column to footing connection. Under lateral loading, we develop plastic hinges here. The red lines that you see here, these are the yielded part of the column. So under lateral loading, this part of the bar yields, provides ductility, acts as a fuse to limit the forces in the structure. Now, if you have couplers within the plastic hinge, different things could happen. So if you look at the figure in the middle and the figure on the right side, you see the figure in the middle. We are using the type of coupler that's called HRC, headed bar coupler. It's a relatively short coupler. So you see the different bars that are spliced. Now within these couplers, we are not able to yield the bar. Okay, so yielding is limited now to the red zone that you see here, but the red zone here is now shorter than what you have the one compared to the one on the left side. Now, if you go to a different kind of coupler, this is grouted sleeve coupler. These are relatively large couplers. You notice that because of the massiveness of the cross section of these couplers, no yielding can occur in that region. So yielding has to be shifted to above and below the coupler. That inevitably could affect the ductility of the column. So that's one of the fundamental reasons for being concerned about, well, what if you use a coupler, we may lose ductility capacity, which is going to compromise bridge safety. Now, the guidelines that we developed, we identified the fact that when you have a coupler, it's not just the length of the coupler. There's a range, there's a region of the bar itself, the splice bar itself, that is affected by the presence of this coupler. So we defined an LCR, which is the coupler region in the guidelines. Also, we came up with equations that account for plastic hinge length change. So the equation that you see in the middle of this slide, depending on some parameters of the coupler, again, I don't have time to get into nuts and bolts of those and define all of those, but what it does basically, it accounts for the fact that the plastic hinge length of the column will be reduced when we have these couplers within the plastic hinge. Also, the effective strain that we can develop in the bars will be lower. So you notice here that we have an equation that tells the designer, if you want to do a strain analysis, how to account for these coupler parameters, the presence of couplers, and account for the reduced strain that can develop. So these are the tools that the designer would need for displacement-based design. So that was as far as the coupler is concerned. As far as the pocket or socket connections, the guidelines, we talked about, you can have an opening in the footing or in the cap beam or both, and insert the precast column. You could have, there are provisions, that specific provision that you say, okay, to form that opening in the footing or the cap beam, usually we use corrugated pipes. So this corrugated pipe, we say how thick they should be. What are the characteristics that they should have? We also identify the gap that you have between the precast column and the pocket itself. So you notice that in the picture at the bottom. And also, how much embedment length do we need? How much embedment length of the column inside the opening do we need? So there are specific equations that we have developed. So the engineer has to satisfy all three of these to make sure that there is enough connectivity between the column and the footing. some reason we can't go to the next slide. Why? Okay, did go. Sure that. Okay, for the connection in the bend cap, again you have a precast column that goes into the bend cap. The precast bend cap now has to be a little wider than normal. And the reason for it is that for all the beam bars or the cap beam bars to go through the connection, we have to bundle them on the side. We cannot allow them to go within the pocket, because if we do that, that would complicate construction. And if you, of course, you have a fully precast column, then you can't even put them inside the pocket. So we have provisions that tells how to bundle the bars, what size of cap beam width do we need, how much extra width do we need to enable the bundling of the bars. So this is the cross section that we show. And also there are other provisions that we provide. At the top of the bend cap, you have to provide some opening so you can place grout or concrete from the top. Again, these are very specific requirement that we have provided. In our provisions, we are addressing different types of pocket connections or socket connection, and they're all shown over here. So they're all included. The provisions are applicable to a variety of these connections. Now, for grouted ducts, as I mentioned, there are two modes of failure. Mode of failure can be the bonding of the bar within the grouted duct, or the grouted duct itself could be pulled out of the concrete, the entire grouted duct. Now, the earlier part of my presentation, I talked about UHPC being in the grouted ducts. In our provision, it's not required that you use UHPC. You can use a regular grout, high strength grout, but regular, not high performance concrete with the fibers, which are relatively expensive. This can be just high strength grout that you can commonly use in concrete structures. So we again spell out what should be the duct material, how thick should it be, how much bigger than the reinforcing bar diameter should be, what is the requirement for the duct size and the spacing of these ducts, because if they're too close to each other, they lose their effectiveness. Also, we have specific equations that talks about the anchorage. What's the anchorage length that we need to provide? So there are two equations. One accounts for bond between the bar, the steel bar, and the grout, and the other one accounts for the anchorage between the duct itself and the surrounding concrete. So the more critical of the two will control what we need to do. Now, all these provisions that I mentioned too, again, they were developed based on a lot of research, and they have been, we have proof tested them in some bridge models. These are large scale models. It's a third scale bridge model. So what I'm going to show you, a video clip here that for a two-span bridge, it's a third scale, and we use grouted duct connections at the top between the columns and the cap beam. We did a series of earthquakes, of course, and I'm going to show you the final earthquake, which was over about 1 G, and this was under biaxial testing, our bidirectional earthquake testing that we did. So let's look at the video. So you notice that the bridge maintained its integrity, that connection, even though we had large deformations, a lot of motion. You notice that the abutment, how much displacement we have. So these are very large displacement, yet the connection was able to maintain the integrity of the bridge. So let's take a closer look Yes, this is being repeated now. All right. This is just a repeat of what you saw. Let me go to the next slide. Let's take a close-up, take a look at the close-up of the connection of the same bridge. So here you have the column, there are two columns with the capping connection using grouted ducts. Notice we had the excellent performance, no damage within the connection itself. That's what happened. Now we also tested grouted ducts in for some reason it doesn't go forward. All right, let me go to the next bridge. This was a steel girder bridge. The other one was a concrete girder bridge. This is a steel girder bridge. This is more than 200% of the design. This particular one is actually 225% of the design. So here again we have grouted duct connection. I'm looking underneath the bridge. Okay, again this is a different bridge. It's a different bridge with steel girders. If you look carefully, you see the steel girders in the upper part of the image. Going longitudinally. Now you have two columns. If you look at the columns closely, the upper part, because we have already applied several earthquakes on this model, we have developed the plastic hinge. Okay, but there is no damage in the connection itself. In this particular bridge model, we also had the pocket connections at the base. There are two-way hinges at the base, but we use pocket connection. So let's see how this one did. So again, this was twice the design, more than twice the design earthquake intensity. Also in another bridge, so these bridges are again they're one-third scale two-span bridges, so they're as real as it gets. Now let's look at some reason it just repeats that. Let's go to the next one. Here we had pocket connections now. We have pocket connections both at the top and bottom. Same dimensions of the bridge, third scale, and again at 200% of the design level, and this is the performance. So there was some plastic hinge damage. Part of the concrete, of course, fell from the plastic hinges, and you saw that in the video. But again, no connection damage. There was no concern about the structural safety here. The bridge maintained its integrity, even though we went twice the design level. Okay, now let's go to the next slide on the third topic. This is about seismic evaluation of the precast column that used UHPC in the plastic hinge. So in the previous one that I talked about, we used conventional concrete, but this one we use UHPC in the plastic hinge as well as CFRP. Now, the idea here is to evaluate this and also see if we can reduce the plastic hinge damage so the bridge can be left in service after the major earthquake. So this is a departure from philosophy, the design philosophy that Professor Itani mentioned, where damage is accepted. Also, a lot of times in bridges, especially in near fault region, the issue we have is that the columns, the bridge has permanent displacement, lateral displacement, to the point that the bridge feels unsafe and you would have to shut it down to traffic. So here we use some post-tensioning using carbon fiber reinforced polymer tendons to recenter the column. So these two innovative ideas were incorporated in this project. So if you look at the column, there's a precast column and the cantilever column that we tested. In the plastic hinge region, we use UHPC. Also, we use pocket connection. So you see we left an opening into the footing, and then also we post-tension this column using CFRP tendons. Again, so there are the two new materials that we have in this column. The UHPC is to control damage, plastic hinge damage, to minimize, reduce. And the purpose of using CFRP tendons is to recenter, bring the column back to its original length. So, as you can expect, we tested this column under near-fault earthquake. Near-fault earthquakes tend to cause major permanent displacement in conventional construction. So we wanted to see how effective these two technologies that we are bringing in are in the eliminating or reducing permanent displacement. So these are the tendons. These are the CFRP tendons. Chances are you're familiar with regular steel tendons, but you're using CFRP tendons. They have very, very high tensile strength, and if you look at load elongation response, they're not that different than steel. They're a little softer, but of course they're not ductile. Once you get the failure point, they fracture. What is important about this is that we use them as in an unbonded setting so that they're effective. And because of the fact that they are made from carbon fiber reinforced polymer, they are non-corrosive. If we use steel and if steel tendons in the column, and if we make it unbonded, moisture will get in and they corrode. But these bars, they do not. These tendons do not corrode. So these are some pictures of the construction of the column. These are some opening that we left at the end so that we can anchor the CFRP tendons. If you look at the picture on the upper right, you notice the column on its side. So the UHPC segment, you notice a slight variation in the color, but the rest of the column was made from conventional concrete. The picture at the lower right shows the post-tensioning process of the two tendons that we use in this column. So, and these are various stages of construction. Here we also use the UHPC for the grout to connect the column to the footing. So you notice that we're putting some UHPC into the opening first. Then we lower the column. You see that in the upper right picture. We lower the column inside the footing, and in lower left, you see as the column is lowered, and then the remaining space is filled with UHPC as well. And the one in the lower right shows you the column after the construction is completed, and of course we are bracing it until it gains its strength. Now, we tested this on a shake table. Again, to limit my presentation, I try to not have that many video clips here, but what's important here, let's look at the figure on the upper left. You're looking at lateral force versus the drift ratio of the column. First of all, you notice that you were able to develop large forces with a large ductility, relatively high ductility. The drift ratio was over 6%. There we began to fracture some of the bars. The bars here were conventional steel bars. And you see, if you look at the right side of the figure, I'm not sure if you can see my cursor, but in this area, that's where we began to fracture some of the bars. And of course, the capacity, the force began to drop. Another important feature that you see here, this run we had a fracture, but in the previous run, you notice the effect of recentering of the CFRP tendon, because you see a cluster of curves going through the origin or near the origin. That indicates that as the loading was reversed, and at the end of the earthquake, the displacement forces circled around here, meaning that there was no permanent displacement, or essentially permanent displacement was removed. Using conventional method of estimating the ductility, this column gave us more than 10% displacement ductility, which is way more than what we normally expect from conventional construction. Now, how about the damage? Remember, there were two reasons for having these two innovations in this column. One was using UHPC to control damage in the plastic hinge, and the other one to provide recentering. The recentering I talked about based on the hysteresis curve. Now, the UHPC effect, this is under about 7% drift. Under 7% drift, conventional concrete plastic hinges look very different. But let's focus on this one. You see there's very little damage and certainly very repairable. So after a strong earthquake, if you go to the bridge site, and this is what you see, considering that there are no permanent displacement, you would say, yeah, this bridge can be left open to traffic. You don't have to shut it down to ambulances, fire trucks, and all the emergency response vehicles. There's some damage at the bottom of the column, but that's minor and that's repairable. In contrast, when for conventional reinforced concrete, this is what we would get under 5 or 6% drift or 7% drift. This is the kind of damage that you're going to see in addition to large displacement. So if that happens, obviously you would not feel that the bridge is safe. So we would shut it down to traffic because it just requires major repair, or in many cases, because we have lost confidence in the system, in the structure, we may end up just demolishing or replacing the bridge. Now, that brings me to the fourth topic of today's presentation. Here, this is something very futuristic now, okay? The idea is to, rather than wasting all this material, because a lot of the bridges that in the US we demolish, they are demolished not because there is anything wrong with them in terms of structure. There's something wrong because of functionality, okay? Because they're obsolete in terms of road alignment, or maybe it could be the width is too narrow and it's not to the in a situation where you can just widen the bridge. So, and you're throwing out all this material, keeping in mind that between 5 and 7% of CO2 emission in the world is coming from cement factory. So the question was, what if we build bridges that can be deconstructed after they have served their purpose? If we need to replace the bridge rather than demolishing it and throwing it away, what if we can reuse it and take it someplace and reuse it? But we also brought in the concept of, okay, what if we also make the damage minimum under earthquake? So with that, we developed these devices that would be incorporated in a bridge column. There are two general types of these devices. One incorporates rubber. So in the picture that you see here, that's a version where we have incorporated rubber in these plastic hinge elements. And the side view on the upper right shows that there's a pipe that goes in there. The steel pipe serves as a shear resisting element to prevent shear deformation. So even though we are using rubber, unlike base isolation that you might be familiar with, where you count on shear deformation to reduce seismic forces, here, no. You're using rubber to reduce damage in the plastic hinge. And we do not want shear deformation, in which case we are restraining that with the steel pipe. So that's one version of it. Moving to the lower part of the slide, there's a different version where we use ECC, engineered cementitious composite, that can minimize the damage. Still cementitious material, but has a much higher resistance to damage because of its higher tensile strength. So the detail for this one would be what you see on the right side here. So it has some similarity to conventional concrete. Now, you notice that in both of these cases, there are holes that are left at the top and bottom. This is where we pass shape memory alloys, super elastic shape memory alloys. The idea is that you control the damage with either rubber or ECC, and you control permanent displacement or reduce it using super elastic shape memory alloy. But you do that only in plastic hinges. Now, the shape memory alloy that is better, has been researched more than any other type, is nickel titanium. So you see a nickel titanium bar in the upper left. And if you look at the stress strain diagram for this, it's the shape of a flag, meaning that once, let's say it looks like a steel when it comes to loading and yielding, but once you begin to remove the load, the curves take a shape of a flag. If this were steel, the curve would continue to come down here and would give us a permanent strain. With these super elastic materials, we don't have permanent strain or very small permanent strain. So nickel titanium is a better known material. We have done a lot of research on that, but there's also a new generation of copper shape memory alloys. These are a lot less expensive than nickel titanium. Again, they have same general characteristics in terms of dissipating energy, but when the stress is removed, the strain is reduced near zero. But so this is the feature we are using to control plastic damage and to provide recentering, these two features. So let's take a look at the cantilever column here. Well, actually, this one is not cantilever, it's part of a bridge that I will talk about more. So this column, what we have done, we have made most of the column, designed it to remain elastic. So the plastic deformation all is taking place over the element, over the plastic hinge element. So you notice how different pieces come together. And these are all prefabricated. So the concept of ABC is there, but you're taking it to the next level, something where the bridge can be deconstructible. So when you put it all together, so you have the upper part of the column, then you have the plastic hinge element. These are the SMA bars, shape memory alloy bars, that are threaded into the footing and connected there. When the whole thing is put together, this is how it looks like. In this particular project, we use pipe pin connection at the top, but you could have a moment connection at the top as well. It's possible to do that. So for the upper part, to make sure that it remains elastic, we use CFRP shells. Again, it doesn't have to be that like that. You can use conventional reinforced concrete. It's possible to do that. We use a GFRP shell for the upper part. So these are various stages of assembly. This is for the cantilever column that we use. So you notice that on the upper left, you see the plastic hinge element where we use ECC. So you see the gray color there. And the SMA bars already connected, threaded into the footing. So this is being lowered onto those bars. In this figure on the upper right, you see a rubber version of it. So this is this one. Instead of ECC, we use rubber in this one. This is something that we have patented. We patented it about 3 years ago. And then, of course, once this element or the other element are installed, the upper part of the column, which uses CFRP shell, is lowered onto the footing, and of course, everything is connected. So we tested individual columns before we took it to a two-span bridge that we tested in the laboratory, supported on 3 shake tables. So I'm going to show you the original bridge. And what I mean by original bridge is that, yes, we put all the components together and we tested it on the shake table. I call that original. But remember, one of the ideas in this project was to make these deconstructible, meaning that, okay, You're going to put everything together, test it to large drift, but then disassemble the whole bridge. Is that going to work? Disassemble the whole bridge and reassemble it, reuse it, put it back together and test it again, see how well it does. So I'm going to show you the original, not the reconstructed bridge, but the original bridge shake table test. You're going to see lots of deformations here. Again, Professor Itani talked about life safety. We certainly did not have any issues with collapse of the bridge. In fact, these steel trusses that you see, the columns that you see, those are our safety system in case, because remember, this is research. There is no guarantee that's going to work. So in case the bridge collapses, we wanted to make sure that the bridge does not fall on our expensive shake tables and damage. But obviously, you notice the gap still there, and there was no problem. Now, let's see what happened to the bridge after we tested this. So we disassembled it, right? We removed all the pieces, and we examined the condition of the pieces. So in some of the columns we had used is the ECC element. You notice the ECC element has some cracks here. But again, these are very small cracks. They're certainly repairable if one wants to repair them. In some of the other columns, we use the rubber element, absolutely no damage. The piping connection that we had up there, it's upright, no damage at all. So this one also performed as what we call capacity protected element. Now, once we remove this element, we also remove the SMA bars. So you notice these are the bars after the bridge was subjected to 6% drift. So these are threaded, remember, but we made them so that they can be removed. They can be removed from the footing and threaded back into that. So that's what we did. After we examined everything, there was absolutely no permanent damage of any sort other than some cracks that you see over here. We did not do any repair, and we reassembled the bridge. Reassembled the bridge, say, okay, now let's retest it. Because again, the idea was that, can we have the constructible bridges? So this is after we put the bridge together. Now this time we went all the way to failure, okay? So this went to very large drift, to 1.2 G. This is the Rinaldi earthquake. The Rinaldi earthquake is a near fault earthquake that causes permanent displacement in conventional construction, but in this bridge it did not. So let's see how the bridge performed. Again, this was a bridge that was disassembled and reassembled and retested to a higher amplitude earthquake. Look at the bridge from the top. So this was about a 70-foot long bridge, about 22-meter long bridge that we tested. So this is again large scale. Now, the concept of using shape memory alloys and ECC, even though not in the form of elements, is something that we have been working on for some time. And we were fortunate to implement that in a real bridge in Seattle, Washington. So I'm going to just show you a couple of slides about how this bridge was constructed. We use nickel titanium in the plastic hinge of the column. We use couplers to connect these nickel titanium bars. These are 30 millimeter diameter, connected to steel bars above and below, because the rest of the column did not need to use this expensive material. So this bridge was built And here you notice a view of downtown Seattle and the bridge under construction. This is the superstructure part of it. Was a top precast elements that were put together. And on top of this, of course, the slab that was placed. Now the bridge was completed. So this is a view of the bridge with the two columns in which we use shape memory alloy bar and ECC in the plastic hinge. And so basically, this bridge has been built. Now it's in service. It was put in service over a year ago, and it's functioning fine. Of course, the next major earthquake will show how well it does, but all the laboratory tests have shown that it worked well. Now, what I would like to leave our audience with is that, first of all, ABC is feasible in high seismic zones. Is feasible. We have proven it over and over. Caltrans has adopted our recommendation and they're implementing it on a whole bunch of bridges throughout the state of California. Some other states have already used them also. In the state of Utah, for example, and Alaska is looking into that. The guidelines we developed was not something that would make engineers to go learn something from scratch. They can learn, they can use the knowledge of they have for CIP construction and take the material that they have presented in an appendix for seismic design guidelines and do an ABC design. Also, we have found that, yeah, it is possible to use couplers. Couplers are feasible. However, you have to account for the reduced plastic hinge length, but we have given the engineers the tools to do that. So they have the equations, so they can proceed with their more or less routine design. Also, we have shown that innovative materials like shape memory alloy are indeed feasible. They're expensive. They increase the initial cost of the bridge by some percentage. However, they will provide a bridge with superior performance to the point that you may not have to spend money on repairing it or even replacing it. Also, we found that CFRP tendons do a good job for recentering. So as an alternative to shape memory alloys, we can use CFRP, unbonded CFRP, to prevent permanent damage. So this is my last slide, Julio, and I guess we can go to the next part of the seminar today to handle questions and answers.
Thank you, Dr. Saiidi and Dr. Itani. And I know that I discussed with Dr. Itani yesterday and showed him how to access the Q&A panel. So, can you access the Q&A panel, Dr. Itani? Or
I can.
Okay. So, yeah, if you share your screen, it won't show because that's a WebEx thing. It doesn't show on the screen. You can go from the top, the questions on the top, and like maybe the administrative and other questions you can probably skip and go to the technical questions.
Okay.
And just click on the question and then read the question out and then answer. That's it.
Okay. There was a question on connections. What is type of the connection better of a girder for the seismic design? And continuous girder would play a vital role in seismic design. As long as you will do the connection as detailed by the specification, we cannot say which one is really better. Both of them will be the same. If you are thinking about the continuity, is that have no connection, that will be the best. The best thing in my mind for a bridge from a maintenance point of view is that to have no connection, because most of the connections would leak, and that will actually cause serviceability problem. That's from the serviceability point of view. But if you do the design based on the ASTRO specification, the connections will be fine. So I'm going down the list now to see the other question. The other question is that for the bridges, what we can consider the R equal to 1 for the elastic design. In that case, cost will be higher. Why? So why not can we consider the R equal to 1 for the building? In that case, we cannot avoid the special detailing for the elastic design for the building and the bridges. Will that be allowed by the code? The answer is we don't recommend that. None of the code would actually recommend to have the elastic design. The main reason for this is that the seismic hazard that we are giving you, that will be an estimate. And most of the time we have seen the actual earthquakes are way bigger than the seismic hazard. So if you did not do a ductile type design, you will have a failure, and we do not recommend that, no matter how the elastic design that will be. So even if you want to do an elastic design, we recommend you to to go through whatever actually the AASHTO specification, and they have the R equal 1.5, and you go through with the detailing requirement for the ductile design of the column as implied by the AASHTO standard specs. So this question is for Dr. Saiidi. For UHPC, is steel fiber is used in the concrete, and how the formation of voids between the steel fiber is controlled. Dr. Saiidi?
Yeah. What is done is the following. To mix this UHPC, you have to have special mixer, okay? Conventional mixer does not do the job. And that's exactly to make sure that you get a complete mix. So we have total connectivity between the fibers and the grout. And as you keep in mind that the UHPC, we do not use coarse aggregate. It's fine aggregate, okay? But it's a special fine aggregate, and again, the design, in fact, when you want to build UHPC, you really have to make sure that you meet those requirements. But the basic requirement among different types of UHPC is that you would have to what they call a high shear mixer, and that way you make sure that you get a very dense concrete, and that's really what provides us with a very high strength, tensile and compressive strength.
Thank you, Dr. Saiidi. The continuation of that, is there a percentage value of the steel fiber that will control the strength of the concrete?
Yes, between 1% and 2%. Okay, there have been, obviously, if you have close to 1%, it's easier to mix it, but typically it's in the 1 to 2% range. And the reason I'm giving you that number is that very high strength that we talked about, the compressive strength, you may not need it everywhere. Okay, in some cases, in some application, the strength could be less, in which case you may go with 1% fibers.
Thank you. The other question is that, and that will be the last one that what I see. Can you explain the function of bearings in seismic load? There are two methods that's how you can do the bearing. You could either design the bearing to take the seismic load, and that's what we normally use if we have a continuous type between the superstructure and the bend cap. is that you will design very similar what I showed you in the video clip. You design the spherical bearing. They are actually spherical bearing to be able to take the the seismic load. They will tend to become expensive. The other thing that what you can allow the bearing to fail, but what you want to provide shear keys that will be built inside the bend cap in the transverse direction and in the longitudinal direction. So that will be your decision what you want to do. And both of these two cases have been used in the field successfully.
Dr. Itani, so we have one more question. So that is regarding the splicing in precast column and piers. So if a considerable height is required, how is the splicing done?
Okay, Dr. Saiidi will be able to answer that.
I'm sorry, could you repeat the question?
Question is about how to splice precast columns or piers where considerable height is required.
With considerable, I didn't understand the last part.
Considerable height. I mean, if the height of the pier or column is more than that is required for a standard column, then how the splicing will be done? So that for precast columns and yeah.
Oh, okay, yeah. It's so you're talking about tall columns and splicing the bars for tall columns. Is that what you're talking about?
That is what I think. Yeah.
Yeah. Okay. That should not be a problem at all. This is because that's more of a standard splicing that has been used for a long time in superstructure or in columns. So it's quite possible. Of course, you will have to brace the reinforcing cages if it's built upright. In many cases, you may be assembling all the bars in a horizontal setting before you make it upright. But now chances are that these splices are outside the plastic hinges, right? Because you're just trying to, let's say, make a very tall column, and plastic hinging typically takes place at the ends of the column, the top and bottom, or just one side, depending on the kind of connection you have. So having splices in the middle or away from plastic hinges, that makes them even less critical. It's quite possible to do that.
So with this, I will take adieu and thank you for attending this closely packed 2 month session that we conducted, and we are overwhelmed with the number of participants that we saw, and hopefully we were able to like at least provide some information that was new and relevant to your practice. So in case you have any queries about in general exam or in general things, you can always mail to support@PRP portal. I can support you on the seismic concrete part for the bridges and everything. We will see what we can do with the lectures that we had. Thank you so much.